Okay, yeah, thank you for the nice introduction. So I'm Masaaki Imaizumi from the U Tokyo and the RIKEN AIP. So and I organize a kind of the theoretical team for the kind of the, like a theory of the machine learning and the statistics. And today, the title is somewhat fancy, like a physics for AI. But it's kind of the series of the kind of the AI4S science seminar for the RIKEN AIP. And I would like to say thank the Yoshida Sensei to start this a nice like a series of the like a seminar. So and basically, so I'm working on the kind of the theoretical aspects of the deep learning and machine learning and statistics. And today I try to explain how the kind of the knowledge of the physics is utilized in the like a recent analysis of the neural networks, especially the dynamics of the neural network. That's the kind of the like key like point of this talk. So, and first of all, that's a brief introduction. So, I believe that everyone in this seminar may understand the kind of the interesting, and the fantastic development of the artificial intelligence. So, and as we know, the kind of the idea is somewhat classic, that appeared in 40 years ago, maybe. But kind of the in about 14 years ago, kind of the deep learning starts. And after 5 years, like a transformer has developed. Then, 2 years ago, 4 years ago, like a large language model, such as the modern AI, has been opened, and we are really enjoying kind of the emergence of the technology of the artificial intelligence. And anyway, so and this kind of recent success of the modern day science using the large scale models is really interesting, successful, and very useful in our daily life and research life. Anyway. So, and this is a very nice technology. That's totally fine. So, and my understanding, also our understanding, our interest is that to understand its principles or the mechanism of the deep nets, transformer, LLM, and AI is still in progress. So in that sense, we try to understand what's inside by using the many knowledge and mathematical knowledge and physical knowledge. That's kind of like our introduction. So, and as we know, AI is a kind of a new phenomena. The typical keyword is scaling low. It means that as we have the larger model size and loss decreases in the power low. And another interesting point is emergence of the intelligence. If your model size is larger than some threshold, high accuracy suddenly appears. It's kind of another interesting phenomenon. And by leveraging this kind of the phenomenon, the modern AI can be a very powerful tool to support our intelligent activities, okay, as we know. So, okay, and we want to understand this kind of new phenomenon, hopefully theoretically and mathematically and physically. So, and here in this talk, we focus on the two aspects, static and dynamic. And static means that it's kind of the property or aspects of the deep learning model, which is already trained. So after many training, we have the nice models, the parameters which globally minimize the loss value, and then we try to understand this property of this model. It's kind of static analysis. And the dynamic is a more flexible. So I mean, learn the kind of the how kind of the behavior of the training algorithms for the deep learning and neural networks. It means that we know the gradient descent algorithm, and we can see that many parameters are updated by time by time. So and we can understand how they are trained and how they get smarter. So that's kind of a dynamic aspect. So in the two large main aspects, and we want to study understand one by one. So and then anyway, now after the appearance of the deep learning, so the deep learning theory has more than 10 years history. So okay, okay.
If you consider the static analysis, basically optimization and the estimation error analysis, they are decoupled.
Basically yes, yeah, yes.
Combine them into single one. So sometimes some error is attributed to optimization error. Sometimes it's estimation error.
Okay.
And also, for example, some layer like batch normalization, they are not updated by gradient.
Okay, yeah, thank you for a great point. Yeah, the current question is that how the in the static analysis, how the estimation and optimization errors are handled, and your point is, and my understanding. And my the simple answer is that the current classical optimization analysis is mainly for the kind of local dynamics. It's kind of closer to the saddle or closer to the minima. If your updates up the parameters are sufficiently close to the some local minima or global minima, optimization analysis can describe the behavior of the kind of the models. However, global dynamics, from the initialization to the kind of the target convergence, has not, fully clarified by the optimization analysis as long as losses are non-convex. So that's my understanding. So that's kind of kind of categorization.
Just the playground.
Sorry.
They have different playgrounds.
Okay.
Dynamic analysis is better than static.
Okay, that's a very critical point, and I will describe why dynamics are important. I do not say more important, but why dynamics is somewhat important in some aspects maybe in 10 minutes. So I will describe why dynamics are necessary. Okay. Anyway, so this is kind of simplified my understanding. So what aspects are kind of more clarified and what is not clarified? So very simply speaking, static is more somewhat a relatively easier analysis, but a dynamic, kind of the global dynamic from the kind of trajectory from the initialization to the target convergence is kind of more complicated or have a neural history. So in that sense, and final performance are much more difficult. Anyway. So, and if you consider more deep, shallow neural nets or deep nets, static analysis aspects are somewhat partially clarified. But dynamic, kind of global dynamics of the training or generalization, it is not fully clarified and partially unrevealed. So, and if you consider more complicated model transformers and rational models, everything is more difficult than the simple neural network. So in that sense, there's a kind of a frontier here, and kind of this side of the this boundary is unclarified, and we kind of theoretical research try to unreveal the kind of the reveal this kind of unclarified vision. That's kind of the just overview. So, in this talk, so I will present the two researches. The first one is here, the kind of a dynamic of the deep neural networks. And second research is kind of not kind of intermediate point between the static and dynamic. It's kind of we focus on the transformers. And I will describe the kind of recent challenges of the kind of try to understand the inference dynamics of the transformers. That's kind of a second research topic. So, and the first one, I will utilize the kind of analysis of the statistical physics to precisely describe the training dynamics. And the second one, I will utilize kind of the nonlinear physics or physics for the complex system to understand the kind of inference dynamics of the transforms. That's kind of the overview of this talk. So, and the first one is the kind of the recent work with my co-author in US, title is like this, but somewhat long, so I will describe this point later. The topic is the precise analysis of the training dynamics of neural networks. And so, and we try to understand, derive the theoretical value of the precise dynamics of the neural network, and they try to understand, characterize the generalization error with the deep and finite width neural network. That's kind of our purpose. And then different techniques, but I will describe this point later. Anyway. Before I say and explain the backgrounds, I mentioned the kind of the setup. Setup is somewhat very simple. So in that sense, I think that the presenting setup first is really easy to understand. So here, our interest is the deep neural network. L is here the depth and the number of layers, and Q is the width, and M is a data dimension, and the W is a weight matrix for each layer, and a sigma function. So this FW is the deep neural net functions with L layers, and input is M dimension. It's a very one of the most simplest definition of the multi-layer neural networks, I think. So, and the setup is very simple. We consider suppose that we have the n IID observed data from some nice model, and we define the kind of the loss function, the square loss function. It's a very simple loss function. And then we try to describe the training, we consider the training algorithm for the weights of the neural networks as a gradient descent. So the t is a discrete time, And this is all the weights. And we update the WT by using like a gradient of L. It's kind of a very simple update, I think. It's one of the simplest case. So, and my goal of this research is that to describe the dynamics of the generalization error precisely. That's a kind of our goal. So, and the generalization error is very simple. For each time t, so we suppose that we draw the kind of the sorry, I did some notation mistake. Oh, that was okay. So this is kind of the like a very simple definition. So we consider the newly generated data samples x and y, then take expectation of the square loss function. So, and we want to know that the value of the generation error for each time. So our goal is that we're going to look at the high dimensional like a limit of the, sorry, I found the type here. This is R here, sorry. Okay, so and our interest is that we consider the infinite limit of the sample size and the dimension m. Then by preserving the divisio to phi, then we try to precisely describe this value, like a limiting value of the explanation error. This kind of our goal. So, and please note that, so we need some exact value, not an order or inequality-based evaluation. That's kind of our goal. That's kind of our setup. Okay. So, and I just mentioned why the precise dimensional dynamics is necessary. That's kind of the background of our this goal. Okay. Okay, and back to the kind of theoretical understanding of the deep learning. One of the grand questions is the kind of the puzzle of the overfitting. So in the very classical statistics and learning theory, it is commonly known that many parameters are harmful for prediction because too large model is easily fit to the training model. They memorize the data, training data, and in that sense, they fail to do a nice prediction with a newly generated test data. It's kind of like a classical, like a common sense in the data science, I believe. But in opposite side, the real, like a deep learning and like AI or transformers, have a very large number of the parameters. It's very powerful, and the more parameters and higher accuracy. It's kind of like a contradiction between the theory and like a practice. So there's some gap. To fill this gap, we have to update the theory. So in that sense, the many theoretical work try to update fill the gap to updating the classical theory to describe the overfitting. But I believe that it is still an unsolved problem question. So yeah, there are many more than 1,000 papers has been published and tackle this question, but it's still many unclear points, I believe. Yeah. Okay, then to understand the kind of to resolve the theoretical question, there are many papers, and they are not every, but maybe more than half papers are focused on the static case. Like our generalization error here, W hat is a kind of trained parameter, and the generalization error is R. These are R can be decomposed into the mainly three types of errors, approximation, and complexity and optimization. So it's kind of a very kind of standard decomposition of the errors. And approximation error says that yeah, how your networks approximate functions. If you nicely choosing parameters and your function can be very complicated, complicated, then it can fit to the functions. Then the complex errors kind of to describe overfitting. And the optimization is that how your algorithm behave with non-convex loss landscapes. So, and there are many papers, and some of them are really successful. And some papers prove that okay, more layers are more effective in approximation. And another paper shows that your SGD, stochastic gradient descent, is a really efficient to escape from saddles, sharp minimums or something. And it's partially described the kind of a nice property of the deep learning, I believe. But still, the overfitting is still like a puzzle, I believe. So to understand the complete understand the overfitting, we need to precisely understand the kind of the training dynamics of the algorithm. So I believe. So, but there are many static-based analysis to tackle this question, but it's not very effective. So, and because that okay, for standardscape of deep learning is really high dimensional and complicated. So, and it's somewhat medically impossible to fully describe the kind of the learning trajectory. So, in that sense, the many analyses have to do the kind of like a loose, a less precise analysis, like inequality based or like a order based evaluation. So it means that the error is no more than this value, but this value is kind of inequality based. So and it's not as tight as the real values. So in a sense, okay, so this is kind of the epoch here, loss is here. The actual loss value is for the red curve, but it's unknown for humans. So, and then many theories try to derive the tight inequality and say that this value should be included in this this interval and here. However, because these dynamics are too complicated, so and our analysis has been not as tight as expected. So, and there are many theoretical hypotheses based on analysis, but most of them are inconsistent to the experimental results. So, and this is a very famous paper that in that age, many theories show that kind of the hypothesis of the implicit regularization, but the hypotheses are not well supported by the experiments, and some paper have criticized kind of the inconsistency and then clear inconsistency, and then it was kind of a very famous paper and kind of a very strong criticism for the statistic-based analysis. So, and then yeah, it's kind of like a limitation of the static-based analysis, I believe. So, and based on the situation, I believe that many theorists have understood that the dynamics can be additional but the key elements to understand the kind of the types of deep learning and or understand overfitting puzzle of the deep learning. It means that okay, so if we consider a static case, only we can analyze that your kind of approximation ability or optimization ability, local optimization ability. But we cannot specify that where the trained parameter is location of the trained parameters. So in that sense, what we can do is that kind of loose evaluation, using the uniform power, the worst case analysis. But this is a really nice theory, but not so effective in the deep learning, I believe. So, and then in that sense, we try to change the strategy, and we should more focus on the global dynamics of the training. So in that sense, we need another tool to describe this behavior. And if we succeed in this full description of this trajectory, it can be a help or fill the limitation of the static-based analysis, I think. Yes, please. Yes.
You argue that for deep learning networks, the uniform deviation bound will be very loose, right?
Yes, yes, yes. Yeah.
But if I remember correctly, 30 years ago for SVMs, the estimation error bound are also very loose.
Oh, well, yeah.
But the argument is that even though it's very loose, like 100 or even 1,000 times larger, because they have the same up and down frequency, right?
Okay. You mean that even though your point is that even though we do not consider the deep learning, but these analysis always.
Yeah, it's always very loose.
Yeah, well, okay.
It's like the U shape or anti-U shape.
Okay, okay.
You
Yeah,
can
yeah.
see some
Okay, okay.
tendency, right?
I totally agree with you. And in that sense, my understanding is that in the 30 years ago, all the theories are loose, but the statistical model is also loose. Just consider the linear regression. In that sense, the model is loose, so theory is also loose, and we do not care the looseness of this case. But in different age, model is precise. It can be, we do not know the theory, but it can easily fit to the more complicated phenomenon. In that sense, the model is so precise. So in that sense, we hope that theory is as precise as the models. That's my understanding. Anyway, so in that sense, that's kind of why we focus on the precise theoretical analysis can cover the kind of the downsides of the classical theory that yeah, kind of a loose theory, inequality based is kind of general, interpretable, is a nice results, but not as powerful as the actual deep learning. So in that sense, we try to change the strategy to achieve kind of more precise evaluation of the loss value. That's kind of our kind of the overview motivation of here. So and of course deep learning neural networks are too complex for the classical theories, and we need to try the strategy and do the precise one. So here, this is the time point of the appearance of the physics. So and there are many challenges, and I believe that one of the most successful strategies kind of utilizing the statistical physics for the deep learning. So as you know, statistical physics kind of like a theory to control the many bodies, infinite elements in some system. So this kind of and it is useful to understand kind of the molecular dynamics or kind of the spin glasses or kind of a material physics. So in here we utilize the kind of the physical approach to the neural networks. So this is a one-page outline of the strategy. Very simply speaking, so what we can do by using statistical physics is that we can express the kind of the macroscopic property of deep neural networks. That's kind of the one-line outline. It means that okay, we have the many large deep nets here. Then so there are many neurons and weights, and we can consider the kind of histogram of the value of the neurons or weights like this. So there are many neurons, many parameters, 1 million, so and we can write this histogram. So this is okay, just a histogram here. But the important point is that if we consider the high dimensional limit in technically like a thermodynamics limit, like a large, like a infinite samples, infinite dimension, and this histogram can converge to the simple Gaussian distribution or some other some simpler distribution. And the key point is that, okay, the original network has 1 million parameters. However, in contrast, if we have achieved the Gaussian case, so Gaussian distribution is just a 2 dimension because only they have the mean parameter and variance parameter. It's somewhat easier. Like just to describe the 2 parameters are sufficient to describe the kind of behavior of this Gaussian distribution. And it's much, much, much easier than the original one because there are million parameters, the 2 parameters. It's very simple. Yes, please.
You said neuron or weight distribution. You said neuron or weight. Do you mean like in the activation? Or are we thinking about inference?
Sorry, always. Sorry, I mean,
So this histogram.
Mm.
You said neurons or weights.
basically weights. Yeah.
Weight.
Okay.
No, activations.
Not the activation.
It can be weights.
Yeah.
It's a very standard to linearize the neural network for theoretical analysis.
Sorry.
Yeah, linearize. Because if you like want Shinoda-san,
Mhm.
Sonoda-san.
Sonoda-san.
Yeah, so, because in deep learning theory, usually you need to linearize it. That's
Okay,
you
okay.
directly consider
Okay, I
the
see.
case.
Okay, I got your point. So, key point is that, I mean, here we do not consider the linearization. The key point is that, okay, here comment is that, we consider the value before the activation. Before activation, the value is by the Gaussian, and the after activation, so this can be described by like this. Okay, this is activation, and okay, and this is kind of some a neural distribution here. Then this is a Gaussian case. So and this is the pre-activation. This is the Gaussian. If this is the Gaussian, and after that, so that's the sigma of x follows the kind of this kind of this is the Gaussian and the push forward measure. Okay, in that sense, after activation, the distribution of the after activation value is the kind of simply transformed version of the Gaussian. We can control the non-linearity here.
Previously, it's a very standard to linearize the neural network for theoretical analysis.
Sorry.
Yeah, linearize. Because if you like want Shinoda-san,
Mhm.
Sonoda-san.
Sonoda-san.
Yeah, so, because in deep learning theory, usually you need to linearize it. That's
The approach is kind of a mean field theory. Mean field theory, yeah, as you raised, and also close to the Sonoda-san's approach, with Richet transformation. I know that. Yes, yes.
may I ask one more
Yes,
question?
please.
I have a concern about this approach because in the beginning you mentioned that you wanted the limit of the number of parameters and the number of data is to convert to something a finite number but not zero, right?
Yeah, I mean,
It's a very standard to linearize the neural network for theoretical analysis.
sorry.
Yeah, linearize. Because if you like want Shinoda-san,
Mhm.
Sonoda-san.
Sonoda-san.
Yeah, so, because in deep learning theory, usually you need to linearize it. That's
Dimension. So in that sense, parameters are always can be infinite.
Yeah, but it's not exactly over parameterized.
Oh,
Because in deep learning theory, if you have a single layer and the width of this single layer is in quadratic of the number of data is exactly over parameterized.
oh, okay, okay, I see. Okay, I
Yeah,
got it.
if it's linear, between linear to quadratic is near over parameterized, but not exactly over parameterized. Because some empirical understanding of deep learning have some experimental evidence saying that if it's really over parameterized or it's between linear to quadratic, the behavior can be very different.
Okay, okay, I see. I got the point. And I have several. Okay, I maybe 5 pages or so. I will represent several like variations of this theory. So I mean, maybe 5 pages. Okay. So anyway, there are several approaches, and as Gansan said that in some cases, like many layers are for the infinite, and in analysis, it's like input layers on the infinite, but it depends on the setups. But the like a common technique is to follow simply follow this kind of we can skip the kind of the many parameters, but we can present like a macroscopic behavior by the simple distribution. But because it's simple, we can describe how they evolve as time passes, like how many how we process updates, like update 6, and we can describe the behavior of this distribution. It's much simpler than the original problem. So, yeah, there are several, still there are many researches, and I just picked out several famous theoretical success to describe the kind of the new behavior of the deep learning. And one case is like a double descent. It is also another by the static case, but the dynamic case it can be more precise. And yeah, in some shallow network, we can understand the double descent by theory. And more emerging topic is the feature learning. It means that the more shallow layer deep nets learn the kind of the fundamental structure of the data. It's very critical to achieve high performance. And by using the precise case, the understanding the feature learning is largely improved, I feel. Okay. I simply also mentioned the kind of the precise analysis can be useful to application to the engineering, especially the hyperparameter tuning. It means that, as we know, learning rate or architecture design is a really sensitive to the result, but it is no a common guideline to select the nice hyperparameters, especially learning rate. So what we could do is that just set the hyperparameter and run the experiment and check the validation error and change the parameter. That's kind of like a classical point. But if we succeed in doing a precise analysis, we can select the hyperparameter theoretically, and we do not have to parameter experimentally, hyperparameter experimentally. It means that if we put the basic information of the architecture data, and if we do the precise analysis, we can predict your actual validation and test error, and no actual learning is necessary here. It's only in that sense. Yeah, some a paper already utilize this technique to to train the a large a model like a GPT or so. And anyway, so and it can be a benefit to the low-cost hyperparameter tuning and actual usage of the large language model, I believe. Anyway, and I go to the more specific research background. And this is kind of almost same thing. And what we can do is kind of considering the high dimensional vector by the histogram, then consider the silent limit and describe the distribution by simple models, a simple distribution case. So I keep here, and okay, this is the key point. And there are many studies to utilize this idea. Then one of the main most famous ones is NPK, linear tangent kernel, but it's a kind of lazy, it's more not so effective as realistic. Okay, and okay, this panel shows that the horizontal direction is like a kind of a complexity of the learning, and the vertical axis is kind of one of the layers, a shallow and deep case. And as Gansan said, the mean field is kind of the most attractive case and really realistic, but it's common for valid for the two-layer networks. So then, yeah, anyway, it's very nice field. And in this case, networks are linear in the measure distribution of the weight. Nothing very easy to understand. So, and more recently, there are several theory appears to which can handle the deep layers. The really most important is a dynamical mean field. It's more that comes from a glass theory or something. So, and it can handle the deepness, but it comes a heuristic case, and the rigorous proof is not so completed. And another case tensor programs is valid for the many layers. And as Gardner said, I in this theory, this theory shows that every bit is diverse infinity. In a sense, it's fully over-parameterized that I just mentioned. So, and here, this is a kind of a nice theory, and this theory can solve, can derive the theoretical value of the neural network, loss of the neural network, even though it is many layers and many updates. And mathematically, it's very rigorous, I believe. But the one downside is kind of it requires an exponential time to numerically resolve the theoretical, numerically derive the predicted value. It's kind of a limitation. In a sense, if we consider adapted more and more time, so it is somewhat impossible to specify this time. So, and our goal is that, okay, we try to reach this case. So, and our goal is that it's possible to analyze the deep neural network in the real situation, like feature learning regime, with reasonable computational complexity. It's kind of like our research goal. Then I go to our analysis. Okay. So we focus on finite widths and many layers and describe the dynamics by the state evolution technique. The state evolution is a kind of not classical, but somewhat the physical notion which can describe the kind of the high dimensional limit of the large scale systems. And state evolution is I wait as SE. And it's kind of the recursive of the sequence of the distributions. And then, and this kind of a nice notion. And then, yeah, I mean, this is kind of a sequence of possibly Gaussian distribution, and it can describe the macroscopic behavior of the neural networks. But the one downside is that if we analyze the state evolution of the neural network, one difficulty is that their distribution is getting far from Gaussian. At the initialization, it is Gaussian. Yeah, here, it's really nice one. But if we consider if we update the parameter many times, 10 times, 100 times, and in this case, the distribution is a more heavier tail or a complicated shape, it is not Gaussian. It's almost impossible to describe the shape of this distribution. It's kind of like a difficulty here. Yeah. And why this is come from Gaussian is that it's kind of a time correlation. So because we update the parameter many times, there are many strong correlation between the many weights of the neural network. So in that sense, it's almost mathematically impossible to track this time correlation because we cannot utilize the central limit theorem here because it's not IID. So, but one nice paper by Montanari developed applied the physical knowledge to the science that we can develop correction to reduce the effect of time correlation, named the Onsaga correction here. So this is kind of a mathematical rigorous notion. And if we put the correction here, we can enjoy the Gaussianity for every time. So initialization is the Gaussian. And if we have the 10 times update, it also still Gaussian. And with every Gaussian with different scale, different mean and variant, it's not possible to analyze, vigorously analyze the behavior of the Gaussian. It's kind of a nice strategy developed by this paper and maybe 13 years ago. So 15 years ago. Okay. It's kind of our own technique. So, and I also put some example of the correction and state evolution. So the original paper study the state evolution with correction in the linear regression problem 15 years ago. This is a linear regression here. It's a very simple case, and this is the penalization. So, and we can consider the iterative algorithm to maybe solve this minimization by this recursive formula. But this is a parameter here. Then this is kind of which is simply close to the proximal gradient descent. But the one new point is this term. This is a correction term named Onsaga correction. So, and this is a very important term. So if we put this term in the algorithm here, then we can enjoy the Gaussian formula of the learning dynamics for the linear regression case. The result is this. So okay, this is kind of the limit of the histogram, a histogram of the high parameter, learned parameter, and we can say that the distribution of this histogram, a parameter value, can follow this distribution. So and the eta is a known function that comes from the L1 penalization here. So, and the W is the standard Gaussian, W is kind of known distribution, it's from the initialization value, and Z is the standard normal Gaussian. Then tau T is kind of sequential updates there's a known variance term. This term is very completely known. So in that sense, we can already enjoy the, okay, W plus tau tz, eta is a Gaussian, and eta is a nonlinear transformation, but it's a simply calculate. So in that sense, we can precisely specify the kind of distribution of the parameter, the distribution of the weights of the linear regression. This is kind of like a classical result here. Yes, please.
This correction values the previous time.
Yes.
Indeed, if we want to evaluate this theta t plus 1, it effectively includes t and values of t and also
Yes, effective. Yes.
some kind of memory.
Yes, you're right. So you're right. And but here, I mean, the important point is that essentially the theta t minus 1 is affected by the theta t minus 2, the previous one. But nominally, only we can refer to theta t minus 1. So that's a simple term. So it's sufficient here. Okay. And Yoshi's comments are very critical. And because this is a linear regression, somewhat simple. So in that sense, we don't have to refer the more far past parameters. But if we consider the more complicated models like neural networks, more complicated reference is necessary. So this is kind of the extension of the previous theory, like a GFOM, like a generalized first order method. So and this is a more general class of the algorithm which can correct a longer time correlation by referring the far past parameter directly. So and to handle the higher order nonlinearity and the strong time correlation here. So and in that case, we need a more larger correlation term. And in that sense, we have to consider every time pairs. Then considering the correction term for every pairs. So in that sense, we need some more matrix version of the answer correction. It's kind of a more recent technology, also developed by the kind of the mathematician and the physicist from the Stanford group. Okay, then I also, yes, please.
Thank you for I don't really understand this correction idea. It's like for the original problem and the original like a gradient descent optimization algorithm, you really have some gradient flow, right? And you mentioned that that one is very difficult to analyze.
Okay, yes.
It will be more and more far away from Gaussian. But then if you add some correction term to make it still Gaussian, that's not the original gradient flow.
It's very critical. Yeah, it's very critical point. And I will resolve this point maybe in 2 pages. Thank you. Thank you for the very nice comment and nice questions. And your comments are very critical, and you can predict my presentation. So, anyway, so and that's just I mentioned why we focus on finite widths and deepness, because if you consider the actual deepness, it's a transformer state, not as a fully connected networks, but deep side widths are almost 100 to several thousand, but sample size feature dimensions are really large. So in that sense, so we focus on the input dimension and feature dimension diversity infinity here. Anyway, so this is our setup strategy. So we consider that this kind of input is many high dimension and many layers, but width is finite, obviously finite. And we consider the state evolution of the pre-activation value, weight of the value before the activation of the first layer. Then considering the kind of high dimension limit, and consider the kind of the state evolution of the first layer. So, and from the second layer to last layer, there's also still a nonlinear high dimension transformation, but we do not consider the state evolution of these layers. It's kind of our strategy. Okay. So, and I showed kind of how to describe the state evolution for this our setup. And this is kind of the answer for the Ganson's question. So, okay, this is the kind of an overview. So, this is the vertical axis is time. Okay, this is the time t minus 1. So they have the activation and time t here, time t here. Then every time, so our gradient descent can calculate kind of the trailing loss and update the parameter for each time. So the first, we put some correction to the kind of the gradient descent. So in that sense, this is kind of a virtual algorithm, not the practical. This is not the gradient descent. This is the corrected version of the gradient descent. And we can achieve the corrected version of the pre-activation here. Then by hydrogen limit, it converts to the Gaussian because of the set limit theorem. Because Gaussian, it's a very nice one. It's easy to track this time evolution. But however, as Pan-san noted, this is the comes from the not graded descent. It's corrected version of the graded descent. So we have to pull back the gradient descent to this another value which correspond to the original gradient descent. It's kind of like a pullback phase. So this is the kind of overview. So this is here we consider the gradient descent here. This is the gradient descent. Then this is the corrected version of some virtual algorithm. Then we take the limit for that is the corrected version of the algorithm first. And if we this formation, then we pull back this result to the corresponding limit of the high dimensional gradient descent. It's kind of like a strategy and answer for the last question. Just a illustration. So it's a high dimensional. Okay. So, and we have the kind of the more, and our actual stability equation has many, maybe 8 lines or so, and I just picked some of the part of them. So, and this is like a row, it's kind of the correction term, like also correction between time. And the tau is a really key term, but I just keep the definition because it's complicated. Anyway, but we can easily calculate this tau here. Then we go this is a correction term. Then we can define like a corrected version of the this is the original preactivation. This is the corrected version. And by utilizing the kind of the past pre-gradients and also correction here. Then UT is like a corrected version of the preactivation. Then if we consider high limit, we can enjoy the kind of the stable Gaussian version of the corrected preactivation, this one, means is 0 and the variance is like this. Then we have to make it back to the theoretical gradient of the gradient descent. So by using this equation, this is a corrected version, and we put this term, then we achieve the original version. So this is kind of the result. So okay, now finally, so we can say that the kind of the actual value of the gradient descent is asymptotically exactly described by the theoretical value, and this term is easily calculated by my laptop. So and anyway, and with some assumptions in that sense, anyway, we can and also we need to note that we have to say that this t square time for calculate this theoretical value. So in that sense, we can calculate the a value of the gradient descent precisely by calculating this numerical value, and it's a kind of tractable for a large t because it's the square time complexity. So, and I also mentioned that, so because we have the kind of the uncorrected version of the preactivation, so it is kind of like a proxy of the distribution of the test data. It's kind of another notion in that sense. So if we have this Gaussian, it can be used to estimate the generalization error directly. So sorry, I have notations type R and here, many R's here, R. Anyway, it's somewhat useful to estimate the generalization error without using the test data. So, and this is the another theorem. So, okay, this is like a generalization error of the gradient descent, but we can estimate this generalization error by this value, which can be calculated without the test data. The only training data we can know the generalization error, test error. So then you say estimate test error precisely. So in that sense, it's somewhat useful for select the hyperparameters here. And this is a simulation, and we can simply find that the kind of agreement between the theory and experiments. So, and the blue is the actual gradient descent implemented by PyTorch, and this is suggestion error. And the green and the reds are kind of a theoretical value, and it is almost fit to the kind of the actual value. So in that sense, we can say that our approximation is kind of nicely fit to the actual data. Okay. Anyway, this kind of the first half of this talk, and but I have less time, so I have to be rush soon. Anyway, so what we did is that we tried to precisely describe the dynamics of the finite this but the deep neural network, and we succeed by using the technique of the GFOM and state evolution. So and I claim that, so kind of overclaiming, but I think that this study is kind of can handle the deepness and the real situation. Okay, and I got the second half, but the time is maybe 15 minutes. So in that sense, I have to rush. The second part is kind of the more related to the transformers. This is kind of another my work with my great professors from Tokyo and RIKEN. So setup is okay, I'm simple. We are interested in transformers. So and as you know, the transformer is the kind of the more modern neural network with each leveraging the kind of the attention mechanism, I think. So the definition is somewhat like common. So I do not describe the detail in detail, but okay, and please we need a notation. So maybe notation is different in this second research. Anyway, then the transformers can be regarded as kind of map between matrices. Their input is d times n matrices, and output is also a d times n matrices. So and x is the input, and we hope that so x is kind of like a set of the d-dimensional tokens. Okay, tokens or like a vectors. Okay, there are many d-dimensional vectors. Now the vectors are m. So we like align the vectors, and x is kind of like a set of the n tokens, n vectors. It's a kind of a setup. So so attention layers are defined by like this, and also the field path layers are defined like this. And as we know that the attention appears in the kind of the original, like here, here, this is like the original figure from the paper which developed the transformers. Okay. So anyway, then here my interest in research is that to understand that the transform is like this, and there's many like blocks or layers of the attention mechanism, attention layer and the field layers, and repeat like many layers many times, and it is the output. So and our interest is that what is the property of the output of the transformers? It's kind of like our like a high level interest. So because like we put like n d-dimensional tokens or data vectors, and we like kind of like transformation is occurred inside the transformers, then like we have kind of output like tokens. Its output is also still like n d-dimensional vectors. So in that sense, we are interested in what is the property of this case. And here, like in this research, we do not consider training. So parameters are fixed, weights are fixed, and we only consider the inference here. Okay, and then there are many, I just briefly mentioned like backgrounds. Okay, and for transformers, there are still like many studies, okay, decomposing the error into the approximation, complexity, optimization, and we try to understand why transformers are so great. So that's kind of like kind of the high level question. And there are many papers, and they are great papers. I really enjoyed the paper, and I also write some of them. So, and some of the part of the clarified advantage of transformer is that kind of like a dimension-free function approximator, and which approximate kind of like a special class of the function, like equivariant functions, or like also in the meta learning aspects, the transformer can learn the kind of the algorithmic aspects of the like learning or something. And anyway, kind of universal approximator of the meta algorithm or something. In a sense, anyway, so there are many kind of the like great findings from this result. But my personal question is that, okay, there are many good points. And in some cases, I derived kind of the convergence rate or kind of like inequality and generation upper bound to show the advantage of the transformers. But my kind of my personal question is that, okay, there are many improvements of the like upper bounds or convergence rate, and it can be like a very great result. But I mean, very intuitively speaking, there seems a kind of like a qualitative difference between the transformers and classical neural networks in a sense. But what's the kind of like a qualitative difference? It's kind of my personal question. Especially speaking, the transformer can achieve like a higher order, like out of distribution accuracy or emergence ability, or many interesting phenomena appears. And how to describe this point? It's kind of like my question. So, and I like explain kind of another like a stream of the research to understand the transformers. And the basic idea is not for the learning theory, but it's more like a interaction system. The idea is that the transformer is a particle interaction system. It means that transformers can mix many particles or data vectors or tokens input in the transforms. It's kind of like a high level insights. Like attention mechanism is a kind of a blender data point for the data points. It means that okay, we input the endpoints to the transformer simultaneously. And as you know, attention is kind of like we follow the other data points and calculate the weights and take a summation average, then like up to some data point. It's kind of like a mixing or like a blending of the data points. And relatively speaking, after one layer, they are mixed some case, and then the many layers they mix and mix and mixes, the many mixes. So in that sense, so it's kind of like a very like a not a specific, but kind of like a special property the transformers, and we try to understand what occurs inside kind of the mixing process or blending process of the transformers in through the like inference So it's kind of like a kind of high level question. So what is an output of the like a blending or mixing? It's kind of like a high level question. Then one emerging research phenomenon is to utilize the kind of nonlinear physics approach, especially nonlinear dynamics case. So so as we know, in physics, there are many like complex system model to describe the kind of interaction of the many particles or many points, like to understand the kind of I don't know how to say I mean polynomial. They are group of the bars in the sky, and the kind of specific pattern appears in some cases. This kind of the pattern maybe analyzed kind of like biological and physical models. And here some researchers try to utilize the kind of like nonlinear physics-based analysis to the transformers, especially the kind of the interaction between among the many particles or tokens inside the transformers. So yeah, anyway, so the one of the famous papers is kind of the Getchkovsky published in the last year. So this paper is followed by the many theoretical studies, and they say that okay, if you put the many particles at the initial layer of the transformers, and they interact like in some cases, and they have some specific patterns. Then if you repeat the many layers, and the patterns are more like can be more specific, and in output case, it's kind of like more like a special, like a form. And this can be used to like a prediction or for a prediction for the next data or something. So in that sense, it's a kind of like this like a kind of the clustering behavior is described by described by the nonlinear dynamical models as the particle interaction. Yeah, this animation is kind of taken from this paper, off of this paper. So this is initial case. They are given scatters, and they rapidly increase like a gap to the several points. And yeah, and then the kind of like speed of the disk clustering has been actually analyzed by this paper.
This phenomenon in practice.
Sorry.
We really have this phenomenon in practice.
Wet question? And I will explain this point in maybe 4 pages. So
Okay.
yeah.
I just feel that it's like the mode class of gun.
Mhm.
If you when you train a gun, it's mode class.
Yes.
You cannot sample from it.
Yeah, I totally agree with your motivation, and all of these studies are on sync to your point. And this theory says that they are supposed to simplify, and they say that every point should be like collapsed. But it's very unrealistic, so I tried to resolve this point maybe in 4 or 5 pages.
Okay.
Yeah, thank you. Yeah, thank you for a great question, really great question. Okay, and this is kind of like a nonlinear dynamical model, which can describe the particle in your system. So time is a continuous time. Time is a continuous. It is a kind of proxy of the depth. Like a long time is a kind of like a representation of the long inference, like an inference for many layers. So and for simplicity, with the token space is like a sphere, like a d minus 1 dimensional sphere here. And we have the n tokens, and each token has a value in this sphere. And for it at that time t, and also indexed by the time tau. Yeah. And for each time, for each the ice particle can be updated at the layer tau by this model. It means that this kind of like a kind of simplified version of the attention layer. So this like exponential term is kind of similarity of the term xi and xj. So this is the weight, the similarity. Then we use the similarity as the weight and take with the average in terms of the xj. Then this value is a kind of like upward direction of the ice token at layer tau. It's kind of like a simplified model. Somewhat simplified, but somewhat realistic. So it can be, so we can see that the update of the ice term is described as the interaction between the xi and xj, and j is taken from the 1 to n. So in that sense, kind of like a way to describe the interaction between particles. So P are great points. And P is defined like this. It's kind of like the token space is a sphere, but if you deduct a P, like a token go beyond the sphere. So you have to project this value to pull back to that sphere. Kind of like projection operator. Okay, and just a point based by the Gansan. And really roughly speaking, the kind of like the study shows that okay, what occurs after many layers, like many inferences. So and the kind of like their nice result is that okay, and then so the output tokens here. Then if we consider the mean field limit, like we consider the n diversity infinity. So in that sense, simply speaking, kind of the distribution of the outputs can be described with a simple like a distribution like this. And in many cases, like a distribution is the somewhat have a simple form. So and we can enjoy the kind of the property of this term. Then the one of the results from this paper is that after many updates, like obtained token distribution is the kind of maximizer of the interaction energy defined by this form. It's kind of like a one of the many results from this paper. So and this shows that sorry, that the argons here. Sorry, I asked arg here. Sorry. Anyway, that's kind of like their result. It's a bit kind of maybe mathematically simple but effective way to describe this point. So, but here I have some motivation. So in a sense, to summarize their result, their like a theoretical illustration is that at the first point, the tokens are like kind of roughly sufficiently spread on the sphere. Then, as the some time passes, the tau is larger than zero, then kind of like clustering appears, and some clustering. Then also, then next, if we update the tokens for infinite times, like many layers, it can collapse to like a single point because the single point, like a Dirac measure, is a maximizer of the interaction energy here. So in a sense, the consequence is that this is the only one after many updates, the mode collapse must occur. It's kind of like a one kind of the consequence of the theory. But however, we know that actual transformer is not collapse. It tends to collapse, but actually not always collapse here. So this is kind of the experimental result. So and kind of like a similarity distribution of the tokens inside the actual transformer, then it means that like a token distribution within transformer like a sufficiently spread, I believe. There's a kind of gap between the theory and practice. So my question in this research is that, so what factor for transformer present the tokens distribution from the like, mode collapse? It's kind of the one question. And another question is that is it possible to prove it's a non-collapse behavior mathematically? It's kind of like my next question. I have only 3 minutes, so it's somewhat very tight. Anyway, so then I want to show. Okay, this is the one-page outline of our analysis. The first our like a claim or take a message is that okay, if we expand the dimension of that token, and this expanding, this prevents the collapse. It's kind of our like claim. So the original transformer, original models, this is the token space. This is actually sphere, and we have the token distribution. But after many updates, this distribution can be collapsed into that's a single like a Dirac measure like this. However, in some cases, we can extend the token space like by putting the extra dimension here. And then in here, in that sense, so the token space that is a mode class appears here. But if we have the extra dimension, and if we fix the marginal distribution along the extra dimension, the collapse does not occur. It's kind of like our like a high level message here in a sense. So token space by collapse by attentions by following their like studies. But we put the extra dimension like by using the marginal dimension fixing. So this is like if this extra dimension prevents the collapse, and we can prove it mathematically. This is a high level idea. And okay, then many of you may thought that oh, this is kind of like a mathematical toy. But what is the actual elements of the transformers? And our like solution is like a positional encoding. So positional encoding is kind of like additional information of the location on every tokens. It means that if we have okay tokens here, then also we also prepare the location variable. And okay, your location is like a first position or 10th position, 1st position. So and we can say that I can put the information here. Then in the actual transformers, we can put this position location on the token. Then we put it the mixed attention here. And this like actual like technique can be described by simply described by this model. Like it's a simple attention with the positional encoding model. It means that okay, we have some like a kernel function g, and we can specify later. And anyway, and this is like original tokens here. Then we also put some of the original location variable here and here. Then this we use this value as like a similarity. Then and then we use that weight to take the kind of average of the like a J's token. It's kind of like a more extended version of the attention models. So, and the design of the G follows the kind of the actual positional encoding. So if we do not have a positional encoding, so G can be fixed as this part. So this corresponds to the original transformer without positional encoding. And the famous positional encoding is the rotary PE rope. And in this case, we can set the G as a dysfunctional form by using the rotation matrix. And also we consider like a distance-based sinusoidal case, positional encoding. So we can put the kind of we previous some function to describe that okay, the similarity of this two tuples can be described by the similarity between the tokens and similarity between the locations. So, and then, yeah, this is the kind of our mathematical statement. So the key point is that, so because the location distributions are already fixed, so in that sense, there exists some kind of the distribution. It's a kind of the push forward of the uniform measure or uniform measure by some of the fifth kind of the map. And this maximizes kind of the interaction energy with positional encoding. It's kind of like our result. It means that after many inference updates of by the inference of the transformers, we can achieve this kind of like a distribution. It means that it is the generated the collapse for the token space direction. But it is not collapse, does not collapse along with location space direction. So we can say the kind of this curtain-like distribution. In this non-collapse case, then we can in that sense we prove that the positional encoding can avoid the mode collapse to the one-point direction, one Dirac measure. Okay, so I skipped here. And I also put the kind of similar result at the fixed prompt insertion. It means that in some inference technique is that we can put some additional prompts on the original tokens and fix the prompts and update token, only update token. It's kind of like another technique. And in this case, we can also achieve the similar result. It means that we put the fixed input here or prompt here, then the output of the transformer does not collapse because of the effect of the fixed prompt. It's kind of the result. Anyway, because time limitation, I skipped some details, but okay, this is our claim. So okay, if we consider the kind of analyze the transformer by the particle interaction system, there can be the theory says that the mode collapse must occur after many inference and many layers. So but it's kind of like a counterintuitive and counterfactual. So in that sense, we developed a mathematical framework to describe the non-collapse distribution. And our consequence is that if we put some extended dimension case, we can avoid the collapse mathematically. Then the example of the dimension extension is the positional encoding and the inserted fixed prompts. It means that our kind of message is that a practical design positional encoding or prompts prevents the collapse in the actual transformers. So with some experiments, what I skipped here, it's almost same to our circuit results. Anyway, so this is kind of like a overview of that's kind of the summary of the second study. Anyway, and I also mentioned the possibility to connection to the more physical knowledge. So, and this particle interaction is kind of like a special case of the Kuramoto model. It's kind of comes from the complex physics model. It can be utilized with biology or society physics. So, and it's kind of like a model of the coupled oscillator, and many patterns of the kind of the stationary situation of the Kuramoto model has been actively studied, especially in Japan, because Kuramoto sensei is a very famous Japanese professor in Kyoto University, and there are many students have many laboratories in Tokyo University or Kyoto University in many cases. And also not only the physics are close to the visible computing. And by utilizing this knowledge, there are many nice knowledge on the phase transition or critical points. Anyway, so these results are specialized to describe the qualitative shift of the models, and I hope that this knowledge is very useful in the field analysis of the transformers theoretically. Okay. Anyway, so this is the final summary, and this is kind of the overview. Then I hope that there kind of there are many deep learning theoretical results, and part of them are really supported by the statistical physics and the nonlinear physics. And because physics are very kind of the nice tool to fit to the new phenomenon like AI, and it was very famous, like useful to like update the machine learning theory and deep learning theory. And I also hope that if we develop the kind of the large language model theory, the physics for the complex systems are really like useful and hopeful to develop the new theory. Anyway, this is kind of like my overview of the physics for AI talk. Yeah, thank you for listening.
Thank you for very interesting ideas. Okay. Maybe time for a couple of questions. Last one.
Thank you. So in the case of mode collapse, the position collapse, okay, so maybe you skip to it, but if you don't have, or when you fix a transformer and you don't have any positional encoding, in a practical transformer, do you observe mode collapse?
Yeah, I mean, so it's kind of like basically yes, but some of the sensitive question. So and there are several variation that okay, and then it is still kind of like under discussion. So in this paper, the very simple setup like this region make which is a diagonal and positive different. So like it tends to occur, but if this one is like a negative difference, something different may occur. In a sense, kind of like I mean, theoretically, there's some discussion about the role of the discrete images. And I mean, reflecting on this result, actually, the transformer, I mean, the actual transformer does not mode collapse so often. But some researchers say that it tends to collapse somewhat easier than collapse than expected in the real transformer is. So that's kind of like a kind of situation.
Theory creating better picture. Because I also want to see the experimental results of the second part. Your theory claims that it's because the real transformer has a positional encoding, so this can prevent the cluster. Yeah, but if you really remove the positional encoding, that means for all kind of transformer, you should be able to observe some.
I believe so. Yeah. This is like a coin model. This is not actual. It's kind of what with the numerical experiment.
I see.
Yeah.
Because you have more layer. It's like because in some slide you have that tau is 0, tau is positive, and tau is infinity.
Okay.
I see. Okay, thank you.
Let's check if there are any questions from the Zoom audience.
Outside. Any more questions?
Yes, this is the result of the mode collapse. It's basically the mode collapse result is basically based on the pre-trained. The training protocol itself is just the next computation.
Sorry, I mean here in the second research for transformers, I mean we do not consider that training at all. So in that sense, like in the theoretical study, they assume that the trained weight is a really like a simple one, like a positive difference something, and we can see that thing. And in a sense, like no training, no weights update here. So
in your case, they're not training, so you pass the initialize.
yeah, cross the initialization, yes.
Another question. Kind of naive question, but I'm originally from physics, so I feel something weird that you would say that the energy maximization, but in physics, energy should be minimized.
Oh, yeah, your point is okay. Well, yeah, I agree that. Yeah, I mean, actually, there are some. Also, they try to kind of like a kind of the sign issue. So, I mean, to define the energy, we have to change the sign, and we can swap the maximum minimization. And
basically, responding to the kind of attractive force.
yes, you're totally right. Yes.
Right. So yeah, very good. So let's thank Imaizumi-san once again.
Thank you. Thanks for making